Hi, my name is David Sharp, and this is project presentation for EEL6509 Spring 2013 semester. The title of the project is Analysis of Channel Coding Techniques for High Velocity Mobiles in AWGN, Rician, and Rayleigh channels. The project I wanted to study was to determine what channel coding methods minimize BER and improve data link reliability in adverse conditions. The adverse conditions studied were the AWGN channel, the Rician fading channel, the Rayleigh fading channel, and also mobiles that were traveling at high velocities which induced a large Doppler spread in those fading channels. The range of velocities I studied was between 100 knots and 700 knots, which is equivalent to 51 to 360 meters per second. This induced Doppler spreads between 150 Hz and 1.1 kilohertz. I wanted to study this particular subject because I'm interested in real-time control of unmanned aerial vehicles. In real-time control of unmanned aerial vehicles, the data link reliability is critical. And the reasons why is if we have high BER and loss of the data link, then we lose control of the vehicle. And in such case, we have either damage or destruction of the vehicle, which is not cheap. And in the case of a crash in a populated area, we may have damage to property or even human injuries or death. The data rate I used in my simulations was 9.6 kilobits per second. For the modulation technique, I chose a binary phase shift keying, BPSK. I chose this because it was highly resistant to errors. I used a hard decision demodulation and soft decision demodulation in various models. The carrier frequency I chose was 915 megahertz. I chose 4 channel coding methods, the first of which was a convolutional encoding with hard decision Viterbi decoding. For this model, the code rate was 1/2, the constraint length k was equal to 7, and the Viterbi traceback length was equal to 96. The second model was a convolutional encoding with soft decision Viterbi decoding. The number of soft decision bits was 3, the code rate was 1/2, the constraint length was 7, and the Viterbi traceback length was 96. For the turbo code, I used a serially concatenated convolutional code. The inner coder was a rate 2/3 code with constraint length k equals 7. The outer coder was rate 1/2, constraint length 7. The overall code rate of the turbo code was one third. The block size was 3072, and the number of iterations was 6. An example of the SECC encoder is shown below. The last channel coding method is a low-density parity check code. This low-density parity check code was based on the digital video broadcasting system standard. It had a code rate of 1/2, a block length of 64,800, and a max number of iterations of 50. Below is a visualization of the LDPC parity check matrix. Existing approaches. Evaluation of channel coding has been extensively performed since channel coding was invented in the 1950s. There are a wide variety of modulation and channel coding and channel models that have been used to examine these approaches. Numerous publications exist documenting the results. This is a common system model used for evaluation of channel coding. In it, we have a data source which is passed through a channel encoding mechanism, and then is modulated, and then passed through some channel model, then demodulated, and then the channel decoded, and then a comparison done for BER. For my performance evaluation, I started with a model to evaluate my channel models without any channel coding, just the uncoded version. And in this model, I have a binary data source, which I pass through a BPSK modulation, and then I have my channel models, and I have a scatter plot so I can examine the received signal, and then a demodulator, and then a bit error rate calculation to determine the validity of the model. My channel model subsystem here is an AWGN channel, and then a Rician channel with AWGN, and a Rayleigh channel with AWGN. All pass through a switch, which I can use this channel select variable to determine which channel model I'll be using in my simulation. I ran my channel model simulation and compared it against theoretical results. The solid lines here show the theoretical curves for the Rayleigh, Rician, and AWN channels, and then the stars show the simulated results at the particular EBN0 values. And as we can see, the simulated values follow very closely with the theoretical results, which proved the channel models were valid. Then I examined the RX scatter plot of the received signal. As we know from BPSK, we expect one dot here at -1 and another dot here at +1. And as you can see, there was a wide range in the received signal, indicating plenty of distortion created by the channel. Since this project is focused on scenarios where the velocity is high, I also wanted to examine the Doppler spectrum of the fading channels to verify that indeed the Doppler spectrum was correct for the velocities. And this is an example for 700 knots. I expected a Doppler maximum Doppler frequency of 1098 Hertz. And as you can see, the expected Doppler spectrum is shown in the red dashed, and then the measured is shown with the blue dots, and they trace the theoretical very well. So we're confident that our channel models are accurate for our simulations. Next, I introduced the channel coding blocks, my channel encoding and my channel decoding to the model. And then I ran simulations through the 4 channel coding methods and through all 3 channels, and then plotted the results. The first was through the AWGN channel. And as you can see here, the blue line is the AWGN uncoded. Then the red line is the convolutional coding with hard decision decoding. And as you can see, it took quite a bit of time, or quite a level of EBN0 before this method could surpass the uncoded method. Then the next in line is the convolutional encoding with soft decision decoding. And as you can see, it passed the uncoded much sooner. And then the next is the turbo code, and the turbo code was very close to the soft decision decoding, but did beat it out. And then the next is the LDPC, and for a value of 0, it was worse than uncoded, but then it steeply dropped off as the bit energy was increased. This is the channel coding simulation in the Rayleigh channel for 100 knot velocity. I had something wrong with my LDPC simulation. For some reason, when it was passed through the Rayleigh channel, the bit error rate was always 0.5, which indicates there is a problem in the model. The probability of a 0 and 1 is equal from the binary data source, so this bit error rate is essentially a coin toss of guessing when it received at the bit error rate. So there was a problem with that, and I was unable to fix it before the due date of this project. But in the Rician channel, this did work, and through other research, I know that in the Rayleigh channel, the LDPC code should perform very similar to what it did in the Rician channel. The convolutional hard decision and soft decision coding was very interesting at the 100 knots. It took very long for it to pass underneath the uncoded BPSK, and then once it did, it didn't get very far beneath it. And another thing to note here is how close it is to the uncoded, and we'll see in the next slide why that's important. The turbo code did very well in this case. It started out nearly equal to the uncoded and quickly fell below and as bit energy was increased. For the Rayleigh channel in 400 knots, again we have the broken LDPC, but then we have the soft and hard decision convolutional encoding, and as you can see now, this time it crosses past the uncoded at approximately the same location, but then it falls off much quicker at this velocity of 400 knots versus 100 knots. Recall, at 100 knots, the lines traced much closer to the uncoded. And again, the turbo code started at about approximately the same place and fell off much faster than the non-iterative convolutional codes. The relay channel at 700 knots again had the broken LDPC, and again the hard decision and soft decision codes crossed nearly the same place but fell off a little bit steeper, and the turbo code again performed somewhat similar. Convolutional coding in the Ricin channel at 100 knots showed a similar result to the relay, where the soft and hard decisions were tracing very close to the uncoded until very high bit energies, and then even when they crossed below, they didn't get very far below beneath the uncoded BPSK. The turbo code performed approximately the same. It was a little bit higher at 0 above the uncoded, but crossed below the uncoded very quickly and had a much better coding gain than the non-iterative codes. The LDPC performed worse than turbo codes for very low bit energies, but once the threshold was crossed, the LDPC code steeply dropped off and outperformed the turbo code. For the Ricin at 400 knots, again we have the same pattern. The soft and hard decision codes cross in approximately the middle here, except for the soft crosses a little bit earlier, but there's much more distance here between the uncoded and the soft and hard decisions. The turbo code looks about the same as at the 100 knots, and again the LDPC performs the same, where at lower bit energies is worse than the turbo code, but as it crosses the threshold it becomes much better than the turbo code. And finally, at 700 knots, again we have the similar pattern here, where hard decision is the worst, soft decision performs second best, and then the turbo code performed about the same, and the LDPC performed about the same. The conclusion is that the non-iterative convolutional codes, the soft decision always seemed to perform better than the hard decision decoding. The performance varied across velocities, which is one thing I found very interesting in this project. The non-iterative methods seem to perform worse at lower velocities than at higher velocities, and they required a much larger bit energy versus noise energy to achieve the BER less than uncoded BPSK. Overall, the non-iterative codes improve BER, but at a cost of larger EB over N0. The turbo code performance was consistent across all the different velocities. The turbo code required the smallest EB-N0 of all methods to achieve BER less than uncoded BPSK. It had very good performance in the Ricin channel, but its performance was degraded by about 10 to the minus 1 when going from Ricin to relay channel. The low density parity check code, its performance was also consistent across different velocities. It required a larger EB-N0 than the turbo code to achieve a BER less than the uncoded BPSK, but it had superior performance over all methods once EB-N0 threshold was reached. Once the EB-N0 threshold was exceeded, it rarely made an error, which was quite impressive. In conclusion, the turbo code had the best BER performance for applications where EB-N0 was near 0 or very low. However, the LDPC code is by far superior when the EB-N0 can be kept greater than the threshold for the LDPC code.